The question of what might exist beyond the universe has fascinated humanity for centuries, standing at the intersection of scientific inquiry, philosophical reflection, and imaginative speculation. As our understanding of the cosmos has expanded through advanced telescopes, particle accelerators, and increasingly sophisticated theories, the mystery has only deepened. At its core lies a deceptively simple question: does the universe have an edge, and if so, what lies beyond it? To approach this puzzle, we must first clarify what scientists mean by the universe. In modern cosmology, the universe is defined as the totality of space, time, matter, and energy, everything that exists and can, in principle, be described by physical laws. From this standpoint, asking what is outside the universe becomes problematic, because the universe already includes all of space-time itself. There is no external container, no surrounding emptiness into which it expands. Instead, the expansion of the universe refers to the stretching of space itself, a concept that defies everyday intuition. According to Einstein's theory of general relativity and the widely accepted Big Bang model, the universe originated approximately 13.8 billion years ago in an extremely hot and dense state. Since that moment, space has been expanding in all directions. Crucially, this expansion does not resemble an explosion occurring at a central point and spreading into pre-existing emptiness. Rather, every region of space is moving away from every other region as the cosmic scale factor increases. A useful analogy is the surface of a balloon being inflated. The two-dimensional surface expands, distances between points increase, yet there is no edge on the surface itself, nor do the points move into anything external to that surface. This leads to one of the most counterintuitive possibilities in cosmology: the universe may be finite but unbounded. In such a scenario, one could travel indefinitely without ever encountering a boundary, much like circumnavigating the Earth without falling off an edge. Alternatively, the universe may be truly infinite, extending endlessly in all directions. If space is infinite, then regions similar to our own, perhaps even identical configurations of matter, would recur infinitely many times, raising unsettling implications for probability, identity, and uniqueness. Yet even in an infinite universe, there is still no meaningful outside. Infinity, by definition, leaves no room for an external domain. What we can meaningfully discuss, however, is the observable universe. This is the region from which light has had time to reach us since the Big Bang. Because the universe has a finite age and light travels at a finite speed, we are surrounded by a cosmic horizon. Today, the observable universe spans about 93 billion light-years in diameter, encompassing billions of galaxies. Beyond this horizon lies more universe, almost certainly governed by the same physical laws, but it is permanently inaccessible to us, as the accelerated expansion driven by dark energy carries distant regions away faster than light can traverse the growing gaps. For many cosmologists, this realization already answers the question of what lies beyond our cosmic horizon: simply more of the same. Galaxies, dark matter, and cosmic structures continue beyond what we can see, fading into an unreachable expanse. But others argue that this answer, while conservative, may be incomplete. To truly grapple with the notion of an outside, they turn to more radical frameworks collectively known as multiverse theories. One of the most influential of these arises from the concept of eternal inflation. Inflation theory proposes that the universe underwent a brief period of extraordinarily rapid expansion in its earliest moments, smoothing out irregularities and explaining the large-scale uniformity we observe today. In some versions of the theory, inflation never completely ends. Instead, it continues in parts of space-time, while local regions exit inflation and form distinct bubble universes. Our universe would be one such bubble, embedded in a vast, eternally inflating background. In this picture, what lies outside our universe is not empty space but a dynamic inflating medium continually spawning new universes, each potentially with different physical constants and laws. Another, conceptually distinct multiverse emerges from quantum mechanics. The many-worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that all possible outcomes of quantum events are realized. Rather than collapsing into a single result, the universe continually branches into multiple, non-interacting histories. Every quantum decision, down to the spin of an electron, creates divergent realities. Here, the beyond is not spatial but ontological, a vast superposition of parallel worlds coexisting within a higher dimensional mathematical structure. Although experimentally indistinguishable from other interpretations, this view radically reshapes our understanding of reality, implying that every conceivable alternative unfolds somewhere. String theory adds yet another layer to the discussion. Developed as a candidate for unifying quantum mechanics and general relativity, string theory posits that fundamental particles are not point-like objects but tiny vibrating strings. For the mathematics to work, the theory requires additional spatial dimensions, typically 6 or 7 beyond the familiar 3. These extra dimensions are thought to be compactified, curled up at scales far smaller than atoms. Some versions of string theory envision our universe as a three-dimensional brane floating within a higher dimensional bulk. Other branes may exist nearby, and interactions between them, such as collisions, could trigger Big Bang-like events. In this context, the outside of our universe would be the higher dimensional bulk itself, a realm where gravity and perhaps other forces propagate beyond our visible cosmos. While these ideas are undeniably speculative, they are not entirely divorced from observation. Cosmologists search for indirect evidence in the cosmic microwave background, CMB, the relic radiation from the early universe. Anomalies in the CMB, such as the famous cold spot, a region significantly cooler than its surroundings, have sparked debates about whether they could be remnants of collisions with other bubble universes during inflation. Other large-scale irregularities, including unexpected alignments and asymmetries, challenge the simplest cosmological models and invite more exotic explanations. Though none of these features constitute definitive proof, they keep the multiverse hypothesis within the realm of serious scientific discussion. Beyond physics, the question of what lies outside the universe inevitably spills into philosophy. Some philosophers argue that the question itself is meaningless. If the universe includes everything that exists, then an outside is a logical contradiction. This view, influenced by logical positivism, maintains that only empirically testable statements carry meaning. Others counter that human understanding has always progressed by questioning assumed boundaries, and that metaphysical speculation, while not directly testable, can still illuminate the conceptual foundations of science. Historical perspectives further enrich the debate. Aristotle envisioned an eternal, self-contained cosmos with no beginning or end, while later religious traditions proposed creation ex nihilo by a transcendent cause existing beyond space and time. In Eastern philosophies such as Advaita Vedanta, ultimate reality transcends the physical universe entirely, with the cosmos regarded as a manifestation of a deeper, non-dual consciousness. Modern philosophical models like the block universe treat time as another dimension, where past, present, and future coexist, blurring distinctions between inside and outside altogether. Ultimately, our inability to directly observe beyond the cosmic horizon may reflect a fundamental limit of knowledge rather than a temporary technological shortcoming. Yet the pursuit of answers continues to drive progress. Future observations, more precise measurements of the CMB, gravitational wave astronomy, and advances in theoretical physics may one day provide clues that reshape our understanding of existence. Whether the universe is all there is, or merely one region within a far grander reality, the question itself remains one of the most profound ever asked, inviting us to confront not only the structure of the cosmos, but the limits of human understanding.